This is a video for lesson 1 quiz, and I'm just going to go over the answers as quickly as I can. I won't waste too much time on them. Anyways, number 1, forces whose lines of action pass through a common point are called, and the answer is A, concurrent forces. And the importance of this is to a concurrent force, for instance, if this force goes through this point, and then this force and this force can go through that point. If you sum the moments about this line, you'll notice that they all equal 0. And let's say you have this force right here. This is the only force that will not that's moment will not equal 0, because it will make a moment around. But since all these are concurrent, or they all go through the same line, then they will none of them will induce a moment about that point right there. So they are all called concurrent. And that is answer for number 1. Number 2 is external loads acting on a body cause it to elongate or shorten. What is this change in size known as? The change in size is known as B strain. Alright, that's pretty obvious. Hopefully, if you don't remember that, go back and read the strain stuff. I understand how it can be a little confusing, but that just is one of those memorization things. Number 3, a material's resistance to deformation is determined by its, let's see, A gets factor of safety, that's no. B, moment of inertia. You can make an argument saying that moment of inertia has something to do with deformation, but that's more in a beam as opposed to what we've been talking about here, which is tension only. So let's go on. Letter C is modulus of elasticity. I think that's the best, because that modulus of elasticity, as I have tried to explain before, is it's stress over strain. So what it means is it's the ratio for the certain types of materials. How fast will it elongate? Will it strain? For instance, steels will be higher if you look at the stress over strain. Steels, it takes more stress to move it, and concrete's a little bit less, and timber's a little bit less. So hopefully that makes sense by now. If not, read over that section again, and hopefully that'll give you some information on that. If not, I'll probably do some videos later on, but not right now. So anyways, moving on to number 4. Number 4 is a load of 10 kips is supported by a 1-inch diameter rod, as shown above. If the modulus of elasticity of steel is taken as 29 million psi, how much does the rod stretch? And this is simple. Hopefully you recognize it's a PL over E over AE equation because it's tension, deformation. And let's see what we have. They give us load, which is 10 kips, which if you don't feel comfortable, 10 kips is 10,000 pounds. We've been working things in pounds, so I'll go ahead and do that. And then L is 10 foot, so let's do 10 foot times 12 inches. Inches per foot. And then area, did they give us the area? 1 diameter, so that's what? 1 inch diameter, is that what I said? Yes, pi d is 1 inch squared over 4. That's area. Let's put that in parentheses so we know that that is area. And then an E is always going to be 29 million psi. For steel. And let's go ahead and do the math on that. And after doing the math, I get 0.0553 inches. And let's just double check on the units here. We went to inches right here, so we're inches times pounds divided by pounds, so that would be then time inches, and this is inches squared. This is squared, so you should just have inches left. I hope that you were following me there. But anyways, I have inches squared right here, because you have inch squared, so that gets rid of that PSI, the SI part. So now you just have pounds, and you have pounds up here, and pounds down here. You get rid of it. You got rid of those square inches divided by square inches. Then you're just left with this, which is foot divided by foot. Foot divided by foot is canceled out, and you just have inches left. So 0.0, and that is C, 0.053 inches. Okay, moving on to number 4. Or number 5, I believe. That was number 4. After cutting a free body diagram of a structure, if the calculated internal forces are negative, then the internal forces act in the opposite direction from that. I'm going to go with B, and here's the reason. After cutting a free body diagram, so you have a free body diagram right here. Let's say it's like this, and like this, and you cut it right here. Let's say it's a simple distributed load on there. And you cut it. This is what you do. And every time you cut, as I had said on an example in the past, is when you cut it, we cut it at this point right here. You have to have a vertical, which I always call V, then the horizontal, which in this case is an axial load or a tension or a compression, so I usually call that P, and then I have a moment. So this is what you will always have every time you cut something. It's the same as a fixed connection. And it says, after cutting a free body diagram of structure, if the calculated internal forces are negative, so if you go through the calculations, and this V, well, the P is going to be 0. The P is going to be 0. The V is going to be positive because those go down. So let's not do that. Let's assume that for some reason we have negative, where we cut it, we have the moment that ends up being negative. So we get equals, let's say, negative 20 foot kips. Well, what that means is, oh, well, the moment's actually going the opposite direction. That's it. And if you got a negative V, that means, oh, my assumption was wrong. And if you want to assume this or this for P, for V, and that for M, you can do that. You can assume anything you want. Just remember, if it's negative, that means you assume the wrong direction, and it's actually the wrong direction. It's not necessarily going down. A little bit confusing, but I think if you look at it, you can understand it. It's not the most difficult thing to understand in the world. Alright, moving on. So that answer was B. Number 6, if a load acts through a body's center of gravity, then the body, 1, has no tendency to rotate. Makes sense. Because if you put a load right through that center of the body, it's not going to rotate. I agree with 1, so let's say 1. Number 2, tends to translate in the direction of the applied force. Well, it tends to move this way. It tends to move like that. I could see that. I guess, yeah, that's all right, but I'm not 100% sure about that. I mean, yeah, it could be. You could say that's a fixed point, so it's not going to translate at all. But yeah, I can see how that works. So we'll keep that in our mind. Maybe 2. Number 3, develops no stress. Well, I don't see that. You're putting a force on it, it's going to develop stress. Number 4, tends to spin about its axis of rotation. If you're putting it through the point, it's not going to spin. So I definitely disagree with number 4. Alright, so we know it's not B, 4 only. We know it's not A because we definitely disagreed with 3 and 4. It's not A. C is 2 and 3, but that's not right. D is 1 and 2. So we're good with 1 and 2. We agreed with that. So the answer here is D. That it will not rotate because it's concurrent. And that's kind of what we have said before, is you don't have any moment. If you don't resist a moment, it's going to rotate. So that's all moment is. It's a moment. It's kind of like torque, but it's not motion, because usually you have a free body diagram and you're in equilibrium, meaning you're not moving, you're static. All right, number 7. How much time we have? We have about 4 minutes left. Number 7, a 10-inch square concrete post supports a compressive load of 20,000 pounds. What is the unit stress of the post? This, I'm not even going to draw anything. This is pretty darn easy. F over PA. Unit stress, so we have 20,000 pounds as a load. And we have 10-inch square, so that's... I never like saying it's 10-inch square, because that sounds too much like 10 square inches. But 10 inch by 10 inch is what I'm assuming they mean. And I'm saying it's 100 inch, so... because 10 times 10 is 100. And we get for our stress of 200 pounds per inch, per square inch, 200 psi, which is letter C. So C is our answer for number 7. Number 8, the yield point is A, the maximum unit stress that can be developed in the material. No, I would say that's the ultimate stress point, meaning the yield. And once again, the yield point is a point where it's still elastic, meaning that if you stress it, it will elongate, but when you stop stressing it, it'll still go back to its irregular. So this is the elastic region, and then if you continue stressing it, sometimes it's like this, where this is the yield point, and this is the ultimate stress. And you want to keep it in here because it starts getting longer and longer, and it will fail your structure because it's too long. But it won't be a, hey, I'm gonna fall and I'm gonna crash into the ground and people are gonna die. It'll hopefully start to bend and people will notice and nobody will get on it. All right, so that's not it. Not A. B, the maximum compressible unit stress used to design a member. No, I will say that's probably not the right answer. Some people times they use ultimate stress, but I don't all the time. You shouldn't, and most time you'll use yield stress. The unit stress beyond which unit strain increases faster than unit stress. Unit strain increases faster than unit stress. Well, that sounds okay. Unit stress at which the material continues to form with no increase in load. The material continues to form with no increase in load. And yes, and I would go with this one, because, like I said before, you have the stress-strain curve. This is stress, and this is strain. And as soon as it goes past this, it will... You don't stress it. You don't increase the stress anymore, but it continues to elongate. So I'd go with D. D is your answer. Alright, and I'm going to go ahead and stop this right now and pick up 9 and 10, the last two, for quiz 1 on the next video.